Good afternoon. So welcome to the first session this afternoon. And we'll have 3 talks in this session. And the first talk will be given by Ahmed. The title is Network-Wide Configurations Synthesis.
All right. Hi, everyone. So today I'm going to talk about how we can synthesize configurations for networks running distributed routing protocols given high-level requirements. This talk is a collaboration with Bertard Sankov, Laurent Van Weber, and Martin Vesche from ETH Zurich. So before I begin about how configuring networks, let's take like a quick review of how typically a network would operate. In this example, I have a very simple network with 4 routers, A, B, C, D. Usually, the network operator is given high-level requirements, usually comes from security or business objectives, that packets have to be forwarded in a certain way in this network. And this network is typically running multiple distributed routing protocols, for example, OSPF, which is Dijkstra-based, BGP, which is path vector-based protocol, and static routes that directly inject routes in the network. And to achieve these high-level requirements, the operator have to go to each router and locally configure each router with some kind of configuration such that the distributed computation of all these protocols will converge to a fixed point that match the high-level requirements. However, this is a not very easy task. Usually, often, the language of these local configurations doesn't match the high-level requirements language, and there are very long configurations that you have to configure for every router. Typically, routers will have from tens of lines to thousands of lines of configuration per router. Any wrong parameter configured there we call misconfiguration, and sometimes not only violate the policy that the network operator wants, but might bring down the network. And as you imagine, it's actually very common for these networks to be misconfigured. And they actually often make the news and bring many major networks down, and also causing major disruptions, for example, for flights or payment systems or voice calls or so on. Some surveys actually suggest that 50 to 80% of network outages are due to human errors. So what's the current practice? How currently network operators figure how to configure a network? They're usually given a network that has running multiple routing protocols. This assumes initially unconfigured. And then some high-level routing requirements. These requirements might be forwarding requirements, how the packet should be forwarded along in the network, or some correctness guarantees, like there is no loop in the network. And they usually manually come with some configurations. And this process is a very tedious process based on the network operator experience and try and error and testing and so on. They come with some configuration. It's hopefully that the routers will accept and compute the right policy. However, this doesn't work. So the current state of the art, in research at least, they're trying to come out and say, like, OK, we can turn this into a synthesis problem. Rather than a network operator manually coming out with these configurations, let's synthesize these configurations. So recently, we have seen several papers in that domain. For example, Genesis in Pobble 2017 can synthesize configurations only for static routes. However, the system doesn't leverage the benefits of using distributed routing protocols like OSPF and BGP, which can be very handy in handling failures and so on. Fibbing was in SIGCOMM 2015, and that system works only with linked state protocols like OSPF, and IS. Recently, also Propane was also a solution that actually works very well, but for BGP-only networks. However, like if you look in practice, people actually running more than one protocol in their network because they have different expressivity level, and they can express different kind of policies, or they have some kind of requirements they impose to them. So someone can say, like, let's use all these systems to do like for each protocol independently. However, that doesn't really work because these protocols have dependencies between them, and you have to really look at the whole picture. And also, what about the other protocols like MPLS and other things that are already running in the network? So what we propose here is a more general system, basically to synthesize automatically configurations for the routers. And we changed the problem here from only synthesizing for a given protocol. Our synthesizer takes as an input a specification of how the network works, regardless of it can be any protocol that is running. And then basically what we're trying to do is here formalize a new problem that say, the input for the synthesizer also not only the requirements, but also a high-level description of how the network operates. And then you just can feed it, OK, I have my network running BGP and OSPF, then the synthesizer will take this as an input. And we choose to get this specification of how the network works and operates, or how the distributed routing protocol works as stratified data log. And then the system, the main contribution for us here is how can we synthesize an input for this data log, or stratified data log. And then our system actually really works at generating real configurations, and we're going to show in the evaluation how we do this. So in a nutshell, like, our system actually can really synthesize inputs for any networks that can be specified as stratified data log. So for the remainder of this talk, I'm going to start with explaining how we capture the network behavior as stratified data log, then how we can express the forwarding requirements, and how these two feed into our system as an input, and how we can synthesize like a network configuration based on these inputs. And then we're going to show at the end how we did some experiments to run it and test it that it actually works and scale well. So let me start first with capturing the network behavior. The key idea here is to use stratified data log. And in theory, you can stratify most of the network protocols as data logs, as stratified data log. And the idea there is not only to run the data log, but the idea there is to have some way of formally specifying how the network works that will be as an input to our synthesizer. So let me take a brief, quick look for those who just forgot how data log works. Here I have the same network. I have some weights for the links, and we're going to compute the shortest path across on this network. So here we have the predicates, like link, and that's basically say like there is a link between these two nodes, and this link have certain weight. And then I can recursively define rules in Datalog that will infer all the paths in the network and the cost of each path. And then we can find which path is the shortest and have the minimum cost. And that's going to be our forwarding state for the network. Then we can do some query. Is there a forwarding path between here or not? And what's the cost of the forwarding path? So to relate this to a network, back to the network, these predicates actually capture the input, the configurations in the network. This is what you can find in the configuration files for the network. And here we capture the computation that the network will do to find the shortest path. And then here we can check on properties on the forwarding plane. This is what have people done so far in the Datalog and networks to do verification. But what we're trying to do here is the opposite, to actually do synthesis based on the same model. So just a quick note, we here actually really focus on the stratified data log. And the idea there is we take this program, we divide it to smaller stratas such that they meet certain conditions. In the paper, we explain more what are these conditions. But believe me now, we just have these boxes, the smaller boxes that we can synthesize for each one of them. Now, what about the requirements? So the requirements are simply formulas on the fixed point of the data log computation. And you can express many formulas. For example, you can specify how the traffic should be forwarded along certain paths, or you can say, I want isolation properties in the path, or have some correctness properties. In theory, you can express many kind of formulas there. What the exact formula is not important. The idea there is actually you can express a wide set of them that which hopefully is enough for a network operator. Now, come back to the core of our system, which is the synthesis problem. Now, in the synthesis problem that we try to define here, we are giving network specification, how the network is operating, and some high-level routing requirements, the formulas I just explained. And the synthesis problem is to find a configuration such that the network will meet these requirements. And we call these the network-wide configuration. Now, we reduce this problem to stratified data log synthesis. And the idea there is the network is specified in data log. And again, here our aim is not to really run the data log, it's just to have some formal specification of how the network will operate. And then we have a query, that are the requirements, that are a query on the fixed point of that program as if you run it. And the synthesis, the synthesis problem becomes, find me an input for this data log program such that if I run this program, the query will be satisfied. And this input can be easily translated back to actual network configurations. So the main problem here that we're trying to focus on really is actually how we can synthesize inputs for a data log program giving a query. And this is a very hard problem because we don't know, I don't know exactly if there's any related work. There's some previous work that did something similar, but doesn't really support negation, which is a really important factor for networks. And the problem is undecidable. However, in the networking world, we have more constraint domain that we can find a solution for this problem. So what we do here is we take this stratus, and we take each one of them, and we take in Datalog, and then we convert them to a set of constraints, SMT constraints. We explain the algorithm a bit more in the paper, and we have to deal with multiple things. For example, how we deal with recursions and loops and so on. And ideally, for each Datalog specification, we come up with certain constraints that match this specification. And the idea there is we feed these constraints to off-the-shelf SMT solver that will find us a model that satisfies all these SMT constraints. And from that model, we can extract a Datalog input that satisfies the query. And the general theorem here, if we find a model that satisfies the constraints, then we can extract an input from that model that satisfies the query. So back to our stratified Datalog program for this shortest path computation. So we generate like SMT constraint for each strata here. I'm going to refer this as box because the constraints themselves are not very important. And then we generate SMT constraints for each one of them. Notice here, the first box is the inputs, which are unknown. These are the ones we want to synthesize and find. And these are the configurations of the network. And the last box, the bottom box, is the requirements, which are given to us. And the intermediate boxes are just the various stages of computation that the Datalog program will compute. So we can start the synthesis process from bottom up. The requirements are known. We go to the first box. We generate a model, a constraints. We find the model. And then from that model, we extract the inputs for the following box. And we go on, and so forth. Just note here, sometimes we might extract inputs that are not valid. And then we go to one box and tell us, oh, these inputs, we cannot find a model that satisfies these inputs. So we have to go back one step and find a different input set. We can go up until we find an input that actually the network configuration, the final network configurations. However, this naive approach will not really work in practice for two main reasons. First reason is not all valid SMT models are really valid configurations. There is a lot of semantics that we lost during the translation, or the Datalog program didn't really capture very well. And the search space is huge. The SMT solver can take forever just to solve a model for one of these boxes. So how we do this? We add additional optimization. We added two main categories of optimizations. The first category are the general optimizations. These optimizations first leverage something called the counter-example guided learning. If we find inputs that doesn't work for us, then for the next time we try to synthesize, we try not to use the same set of inputs. And the second part is partial evaluation. And the idea there is to try to compute as many values as we can outside of the SMT because it's just faster. And the second part is more network-specific optimizations. And in this part, we use domain-specific, we add additional domain-specific constraints to our model. And the idea of these constraints is only to make the SMT only considers the models that are relevant and correct from a networking point of view. And the second part is input constraints. And these are actually at the inputs for each strata to really make sure that the inputs are generated are always correct from a networking point of view. For example, if you're computing the shortest path and you're computing the link weights, just don't compute negative values, just compute positive values, for example. So we actually took the system and we tried to run it on real networks and see how it behaves. So we implemented the system using Python. We use Z3 as our off-the-shelf SMT solver. And our system actually outputs real Cisco configurations that you can run in the real Cisco routers. And for the network specification, we fed it as an input specification for IBGP, single area OSPF, and static routes. So, and then we did two sets of experiments. In the first set of experiments, we tried to see if our system will work for a real network that is already in production. And in the second set of experiments, we tried to see how well will our system scale given some synthesized networks. So we used Internet 2, which is a popular network that's been used in the US to connect all the US universities. And we tested on two dimensions. The first dimension is how many routing protocols being used in the network to implement the given requirements. And the second set was how many requirements we can implement. I just want to mention here, in the networks, usually requirements can be grouped together into equivalent classes. And basically, these are the set of requirements that basically trying to do the same thing. And some surveys suggest that in production networks, there is about a dozen requirements, equivalent classes of these requirements in any network. These equivalent classes might map to one requirement per each or might map to 1 million. It depends on the network, really. So our system actually can work really well for static routes. In a few seconds, you can actually generate, even for the largest set of requirements that match the real production network, in like 4 seconds, you can get reasonable configurations. And if you're using all the protocols that we support right now, or static OSPF and BGP, you can finish in less than 1.5 minutes. So we take it, next we take it a step further and see how about synthesized topologies that are larger than this. So we use grid topologies or various sizes. The largest grid we have used are 8 by 8 routers, or 64 routers. And then we used only for 10 traffic classes. And then we can see here that our system actually can scale well. For static routes, we finish for our largest case in less than 1 hour. For static and OSPF, we finish in then 24 hours. Take in mind, this is actually an offline system. Like usually, network operators will get some requirements. They will try to implement it and then forget about it until they get some new changes. So our future work will include more optimizations to bring this number down to make it even faster. And this comes to the conclusion of my talk, that here I showed how we can actually synthesize configurations for any protocol that can be expressed in stratified data log. And you can find more information about this in our website.
Thank you. And we have time for questions. Yes, please.
Hello. Hi.
Hi.
Nice talk. I have a couple of questions. So the first one is you took an MP complete problem and reduced it to an undecidable one. And the question is, does this mean you learned something about what's decidable about synthesis for Datalog?
No. So yes, it's correct. This is an undecidable problem, and we state this in undecidable problem. However, with the optimizations we have, we were able to reduce the search space so that for the practical cases that we care about, we were able to find solution within a reasonable time.
Yeah, I guess my question is like, does this bring us maybe closer to understand what's decidable about stratified data?
I don't think we are closer, but for most of these undecidable problem, we always find some niche cases where it would work for this specific case. But for the general case, I don't think we can generalize out of here.
And my second question is, you motivated the talk by mentioning error in configurations.
Yeah.
So all those errors are actually, they only happen because of failures, like things like routing loops?
No. Most of them actually because configurations, yeah, there is some failures happened during this, of course, but the kind of errors I was referring to here mostly like operator error. For example, one of the Amazon outages was because the network operator just fed the wrong parameters for a configuration file. So in a level 3 example, the operator wanted to change the capacity on one router, but end up changing one other flag that will drop all the VoIP traffic in the US and then end up with huge outages for VoIP.
So, but I guess my question is like, what prevents your tool from generating just entirely static routes and then having very bad behavior under failure?
Generating all static routes is it's one solution. It works. But however, in general, people deploy the distributed routing protocols because they are very resilient to failures, and the network can handle failures for you. You don't have to deploy any controller external to the network. If you have static routes, then basically you have to really watch the link state all the time. And if something failed, then you have to switch the routes to divert around this failure, for example. But in the general case, if you run OSPF really converges really fast. And then if some failure happens, then the network will take care of it, and you don't have to intervene as an operator to fix this problem.
Yeah. Just very quickly, with that Internet 2 experiment, how big was it?
I'm sorry?
The Internet 2 experiment, how big was that?
How was big?
How big? How many routers? I mean,
so about 9 routers.
So it was the 9. That picture was the actual.
Yeah.
Okay. And because you were getting exponential times in kind of a 64 router network, strikes me as being pretty impractical.
We actually kind of like stress test our system more than we should in the grid topology, because the grid topology have higher density because every router is connected to others, like 4 routers inside. So that's why it's a bit like maybe a bit slower in the grid topology, but we really wanted to really see how the system would scale in worst case scenario.
So in real life, what's the smallest kind of niche application where this could be useful?
So,
like how close are you to being?
There is a famous repository for they collected more than 200 to 300 real network topologies, and for that repository, I think it's called Internet Topology Zoo. We can cover about maybe 50 to 60% of the topologies there that already we know about in production.
Okay. Thank you, Ahmed.
Thanks.